Hey everybody, so today we're going to be looking at the equation for heat or specific heat. Kind of goes by both names. If we know specific heat, we can always measure, measure out mass, change in temp, and try to figure out the amount of heat gained or lost by a substance. Or if we can calculate, if we can figure out the amount of heat gained or lost, we can figure out the specific heat of an unknown substance. That is used forensically to kind of determine materials at different crime scenes, stuff like that. So really going through it, kind of explaining it here. So Q, that's our heat. That's our thermal energy. It's measured in joules. All energy is measured in joules. Doesn't matter if we're talking about kinetic, potential, chemical, thermal. It's all joules. Mass is given to us in grams, or it can be in kilograms. One thing to keep in mind is whatever unit our mass is in, it has to match the units used for our C, our specific heat. So say specific heat. Wow, that's kind of messy. All right, I need to work on that a little bit. All right, the unit for that can either be joules per gram degree Celsius, or it can be joules per kilogram degrees Celsius. The big thing about this is these two units for mass and specific heat, the mass here, they need to match. It would probably be easier just to change the mass, to go from grams to kilograms, move your decimal 3. So let's say we have like a paperclip weighs 1 gram. To move it into kilograms, we're going to move our decimal 3 to the left. 1, 2, 3. So our decimal goes there, and we're going to need those 2 zeros there. So that would be 0.001 kilogram. Or if I'm working with a 30 kilogram weight, to convert it the other way, we're going to move our decimal 3 to the right. So in this case, 1, 2, 3. We're going to add 3 zeros there. We're really working with 30,000 grams. All right, that's just converting that. Change in temp. So the triangle and the T go together. This is change in temp. So changing means that it has a starting value and an ending value. To find it, we're going to take our final temperature and subtract our starting or initial temperature there. Measured in degrees Celsius. So let's go ahead. You could use Kelvin here because a change of a degree Kelvin is the same as a change in degree Celsius. And so the degree Celsius here could easily be switched out with Kelvin. All right, so let's take a look at a couple of examples here. I am going to put Q equals MC triangle T. I'm going to keep that up there. But now let's go ahead. Let's take a look at... let me kind of redo some stuff here. That'll work. All right. So question number 9 there asks, so the specific heat of ethanol... go up a little bit. All right. Specific heat of ethanol is 2.46 joules per gram degrees Celsius. And they want to find the heat required, so they're looking for Q in this case, to raise a temperature of 193 grams, so that gets us our mass, from 19 degrees Celsius to 35 degrees Celsius. So we're starting at 19, we're ending at 35. So our change in temp is equal to 35 minus 19, which should give us, do that down here quick, 6, 2, 1, 16 degrees Celsius. All right. Since we're looking for Q, we don't need to rearrange the equation at all. I'm looking here. So Q equals, take our mass, 193 grams, times our specific heat, which is 2.4, make that decimal bigger, joules per gram degree Celsius times, sorry, change in temp, we figured out was 16 degrees Celsius. All right, so just like with any other equation, there is a way to make sure we are doing it correctly. So grams up top here, grams on the bottom here. That is supposed to be a G, not a Y. Let's try to just do that. All right, degrees on Celsius on top here, degrees Celsius bottom there. Let's go ahead and cancel those out. So the units I'm left with is joules, which is what heat's measured in, so we're good there. So let's go ahead and open up a calculator. All right, so we said we had 193 times 2.46. Let's go ahead and just make that a little bit. Nah, that didn't really work. That's fine. Times 16. All right, so the heat energy gained by the ethanol is, oh, lost it there. 7,596.5. 7,596.5. And once again, our unit is joules. All right. So really looking at the thermal energy gain there in number 9, that's really what we're looking at, is at 7596.5.48. Same thing. You know, that's a decent amount of heat. Whenever we're working with water, which you will in some of these problems, the amount of heat needed to that the water needs to absorb to change its temp is really high. This is about medium, 2.46. That's about an average, a medium, middle of the road specific heat. So it doesn't require a lot of energy to change temp, but it's more than, say, what we're going to find in our next problem. So let's go ahead and clear that out, and let's look at number 10 down there. Let me get my Q equals MC triangle T. All right. So number 10, when a 120 gram sample, well, grams is mass, so I'm just going to write that down, of aluminum absorbs 9,612 joules of energy. All right, so in this case, they're giving us energy. Energy, in this case, it's implied that it's thermal energy, so they're giving us a Q of 9,612 joules. And its temperature increases from 25 degrees Celsius to 115. So we're starting, so change in temp is equal to, all right, so 115 minus 25, 55 is 0. 11 minus 2 is 9. All right, change of temp, 90 degrees Celsius. In this case, they're looking for the specific heat. All right, so a couple ways we can go about doing this. We can either algebraically rearrange the equation to get C by itself before we even plug any numbers in. I like to put the numbers in first. So that's what I'm going to do. All right, so Q, 9612 joules equals to the mass, 120 grams, times specific heat, which is what I'm looking for. So leave that to capital C. Times change in temp, we said was 90 degrees Celsius. All right, so now I need to get C by itself. Well, if it's being multiplied by 120 and being multiplied by 90, to get C by itself, we just have to do the opposite, which is divide it by 120 and divide it by grams degrees Celsius. And what I do to one side, I'm going to have to do to the other. So 120 grams times 90 degrees Celsius. So that cancels there. That's canceling there. All right. So now I have C is equal to 9,612 joules divided by the quantity of whatever 120 grams times 90 degrees Celsius is. One thing to point out here, joules, grams, and degrees Celsius, none of those can cancel. So right away I know that joules over grams and degrees Celsius is the label for my answer, and that's what specific heat is in anyway. All right, so this case, cleared that out. So we said we have 9,612 divided by, can you change the scientific quick? I'm going to start over. All right, so let's go 9612 divided by parentheses 120 times 90, closing parentheses, equals 0.89. All right, bring that down there. So my answer here, the specific heat of aluminum, 0.89, and once again, joules, oh, missed it there, grams, degrees Celsius. Joules per gram, degrees Celsius. All right, so that's the specific heat for aluminum in this question. The metals we're going to find, typically they're going to be low, generally under 1. Some of them might go over. When we start working with more covalent compounds, you know, the ethanol stuff, specific heat will be higher, 2 to 3. Water, though, highest specific heat out of just about anything we're going to work with, 4.184, which is pretty big. All right, so that's really the specific heat equation. One important note here, when we're doing calorimetry, it involves kind of a two-step process, and I'm going to go into that later on. So anyway, thanks for watching. I hope that helps out.